the test 1 and 2, it will be in the same, it will have, the same format as the ELE 105. You have 70% long type questions or problems and 30% 10 multiple choice questions. We'll see about, the test 3. I don't know yet. Let's see if he is approved or how it's approved, and I will let you know the format for test 3. But until then, probably, close to, the beginning of December, I know that, the 2 test has been approved and is on ground proctored. Means that we'll end up with, the same, 50 minutes for test 1 and 2. And the format is like ELE 105, long type questions and multiple choice questions. Did I answer the question, Shan? Okay, perfect. Now I will share my screen with you, and as I mentioned yesterday, I'll do some examples, in-class examples. Make sure you have the piece of paper or something that you can make some extra notes. And this is the basic circuit that has a Zener diode. To remind you about the Zener diode, always it will maintain a constant voltage, which is actually the voltage across the VZ. When a positive voltage is applied to the cathode and a negative voltage is applied to the anode. Now to plot the characteristic, the IV or the VI, I mentioned that I prefer to say it, the IV, because it's the current as a function of the voltage. But in some other textbooks, you may see a VI has, the same meaning. You notice that on the right side of the graph, the diode, it will behave as a regular diode, means that if it is in forward bias, and you notice that the abbreviation I use, the forward bias, the diode, it will behave as a regular diode. There is no change in the behavior of a diode if it is in forward bias, means that the positive is applied to the anode and the negative to the cathode. What's the most important application for a Zener diode? When it is supplied or when it is used in reverse bias. And you notice that if the voltage is in reverse bias, or on the left side of the y-axis, the diode is in reverse, means that the cathode is connected to a positive, and I'll put a note on the top, and the negative is applied to the cathode. Remember that those basic circuits, and I'll give an idea about the application of using a Zener diode. Suppose that I have a circuit that is already supplied by 20 volts, but a sub-circuit or an extra system or an extra device is required to have just 10 volts. Do you need to have an extra rectifier? Probably not. The easiest way to make 10 volts available from 20 volts power supply is to use a Zener diode. That's the voltage VZ. I will choose the VZ of the Zener diode, that it will have a steady voltage as 10 volts in the example that I made, which will impose the two limits in terms of the current. You notice that I'm having the IZK, and remember that I was talking about that knee of the graph. That's why, in order to avoid any confusion in terms of the uppercase or the lowercase, the minimum and the maximum current that can flow through the diode. In order to place the diode in the Zener mode or in the tunnel or avalanche mode is to maintain or to have the voltage applied to it greater than the VZ. Means that if I will choose, the VZ, or, if that's, the VZ or the voltage across the diode for 3 volts, 5 volts, 10 volts, 20 volts, and so on, you notice that the current or the minimum current that must be maintained is the IZK. The maximum current is limited by the maximum power dissipation by the diode. Again, we have, a device or any device that has a voltage across across it, and a current that flows through it, it will dissipate power. What that means, the limitations or the power limitation in terms of the current, in this case, the minimum and the maximum current has to be taken into account. Based on this basic circuit, there is nothing to be memorized, is the KVL and KCL. And I'll show you again, step by step how to apply those equations that helps, to solve or to calculate the input min and max values, the resistance R, or the minimum and the maximum value for the load resistance. You notice that I can make, or I can divide, this circuit in 3 sub-circuits. One on the left side of the resistance and diode, we have the voltage source, means that we can determine, or we have to determine sometimes, what will be the minimum and the maximum input voltage for a given resistance and a given Zener voltage. On the right side means that anything that is connected between the 2 terminals of a voltage becomes, a load. In this example, that's, very basic. I'm using, the RL as the load resistance that it's connected across the diode. Sometimes it's called, the shunt. Remember that, and we spoke about, the shunt configuration or parallel configuration has the same meaning. That's why some other references, some other textbooks are referring as a shunt configuration for the Zener diode, because the RL is connected in parallel with the Zener diode. Now, for the first part or the first type of problems, let's say for a given resistance, means that the resistance R is given, the VZ is given, for example, is 10 volts or 5 volts, and we would like to determine what is the input voltage, the minimum and the maximum input voltage that can be applied to the circuit in order to maintain a constant voltage across RL. I will define that as the VRL, or the voltage across the resistance RL. Now, I'm looking again, in the characteristics, the characteristic of a Zener diode. Again, it's mostly used in reverse bias, means that on the left side of the y-axis, and we can define the load line. That's why I'm introducing, the load line and the Q point or the question point of the circuit. To remind you, we mentioned that, the biasing of a circuit. In terms of bias in electronics, usually means that the value of a DC voltage for a device to operate or to work properly. In the same way, we can determine what is the load line, which can be defined from the KVL that is applied to the inner loop. Now, applying, the KVL on the inner loop, we can find that, the input voltage or the Vin is equally the voltage drop across, the resistance plus the voltage VZ. VZ it's given, or we know, the voltage that is required for a circuit, means that from the main equation we can determine the V in as the Vz plus the voltage across the resistance. You notice that in this graph I represent the Vz and the V in. V in always has to be greater than the Vz. If the V in, and I'm making an assumption that the V in is less than Vz. You notice that the the supply voltage is less than Vz, means that the current that flows through the diode is minimum, or it's very small. We make the assumption that if the V in is less than Vz, the diode, it will act as an off state, or a switch turn off. Means that there is no current. We did this experiment, and we figured out that the current in this region, if the diode is in reverse bias, it's very small and is negligible in our calculations. Now, from this equation, we can determine what is the IT, or the current that flows through the circuit. You notice that I use, the IT as the total current supplied by the voltage source to the entire circuit. Now, I may apply, the KCL in this node. You notice that the current is divided in two currents, or two branch currents, the IZ and the IL. I labeled, in the same way, IL, RL, and the VL, and the IZ, VZ as the parameters for the Zener branch. Now, in this configuration, let's say, that's, the basic configuration. I'm not going, above, this basic configuration. And I mentioned that there are three types of problems that you may see it in the assignments and tests. The first problem is, given the resistance R, given the Vz, find the limits, or the limit, the minimum and the maximum voltage that can be applied to the circuit to maintain a constant voltage across the load. Suppose that the resistance is 200 ohms, Vz, suppose that is 20 volts, PD is 5 watts, which is the same with the PD max. Remember that we talk about this notation, PD in the specs of a diode, which has the same meaning with the maximum power dissipation of the diode, and the minimum current, or the IZK, or the knee current, which is given as 5 milliamps. I try to group those equations, or what we are using in these circuits. That's the KVL. I mentioned that the KVL is applied in the inner loop, and I may try to emphasize again, I'm applying the KVL in this inner loop, or the first loop, which has the voltage source in it. And the other equation is in terms of the current, means that the IT is the IZ plus the IL. You notice that this current, or the IT, is the IZ plus the IL. Means that I'm using those two equations only. Those are very useful equations. In top of that, we have to have the two conditions. The V in has to be greater than the Vz. I'm looking back in this diagram, and that's the condition. The V in has to be greater than the Vz. Means that we have to make sure that the diode is operating in Zener mode. Another condition that has to be met, you notice that the IZ has to be maintained between the two limits. I'm having the minimum and the maximum current. Means that that's the span, that's the range of the current that must flow through the Zener diode in order to maintain a constant voltage. That's why I group them as as a condition in order to maintain a constant voltage across the load resistance. Now, you notice that in this given equation or a given problem, let's say the resistance is given, the voltage Vset is given, the power dissipation and the minimum current. The question is, you notice that this maximum current is not given. But I mentioned that is given the power dissipation or the maximum power dissipation. Knowing the maximum power dissipation, knowing the Vz, we can determine what is the limit of the current that can flow through the diode. Remember that the Iz max or the maximum current is the power or the maximum power dissipation across the diode divided by Vz. It makes 250 milliamps, means that I'll take this maximum current Izm to determine what is the minimum and the maximum voltage applied into the to the circuit. First of all, we have to look, in the diagram and find what is the minimum voltage. Means that I have to use, the minimum current to determine the minimum voltage drop across the resistance RL. Again, for the first diagram, and I may, delete the RL here. You notice that I'm having, the current that flows to the resistance R being the same with the current that flows to the diode, the Zener diode. Means that I'm using the minimum current, which is one of the two conditions. You notice that the first part of the equation has the Z less than or the Iz or the current that flows through the diode has to be greater than the Izk, which is the minimum current. Knowing that the minimum current and the resistance R, we can determine what is the minimum voltage drop across the resistance R. Means that using the minimum current, the Izk, using the resistance R, we can determine that the lowest voltage drop across the resistance R, it's 1 volt. Now, going back to the useful equation, you notice that I'm using, this first equation to determine the V in minimum is the Vz plus the minimum voltage drop across the resistance, which makes, 21 volts. On in a way or solve, the same equations, except that I will determine, or in order to determine the maximum interval voltage, taking into account, the maximum current, we just determined that the maximum current is 250 milliamps. Knowing the maximum current, knowing the resistance R, we have to determine what is the VR max, or the maximum voltage drop across the resistance R. Knowing the maximum voltage drop, which is the Iz max multiplied by resistance, gives you 50 volts. Knowing the maximum voltage drop due to the maximum current that can flow through the circuit, we can determine what is the input voltage or the maximum input voltage as 70 ohms. Now, in order to make the diagram of the input and the minimum and the maximum voltage, I may make this range, means that the V in max, and on the other side is the V in min. The minimum voltage will be 21 volts and the maximum voltage will be 70 volts. In this way, we can determine what is the range of the voltage that may be applied on the circuit to maintain the given voltage, or to maintain the voltage across the resistance as the 20 volts for a given load. Now, the second example, or the second type of problem, means that is given, or we know the input voltage. Now that's the input voltage. We know the VZ, and for a given load. Means that those are, the given information, or what we know, what is required for the circuit, and we have to determine what is the value of the resistance that has to be added into the circuit in order to maintain a constant voltage. Again, we are making the assumption that VE is constant and the RL is connected between the two terminals of the Zener diode. In this example, the V in, for example, it's 5 volts, VZ is 20, IZK is 5 milliamps. I use, the same value. I mentioned that the IZK is, few milliamps, usually 1 to 10 milliamps. That's, the range that I'm using in problems. PD, it's 5 watts, and the RL is 200 ohms. Now we have, to make the same way or the same approach. You notice that in this given data, the IZ max is not given. If it's not given, we are making we are using, the known equation that the PD max, or simply the PD, is the IZ multiplied by the VZ. To determine the IZ current. Now, let's go back to this, this diagram. I mentioned in class that, in example 2, we are making the assumption, and this is what we have to make in these specific problems, that we are choosing, we are choosing the IZ halfway between the minimum and the maximum. Means that I'm having a full range of the IZ to move lower up to the IZK, and to move higher up to the IZ max. Means that in this specific problem, or this specific example, I'm choosing the IZ as the IZ max divided by 2, or halfway. Now, to be more precise, but is not required, I can take, the IZ max minus the IZK and divide by 2. But remember that IZK is very small, means that we can neglect, the value of the IZK. And to simplify our calculations, I will say that we have to choose the IZ as the IZM divided by the by 2. Means that I'm choosing the IZ halfway between the IZK and the IZM. That's, again, specific for this type of problem, when we are looking to determine the maximum or the resistance value, given the V in, given the VZ, and given the resistance R. Means that we are making this assumption, just for this problem only. IZ max divided by 2 is 125 milliamps. Remember that, and I put that in writing, the PD, or the PD max, in the given statement of the problem, or the given information from the specs of a diode, PD is the same with the PD max. That's why I can use the PD, or the PD max, to determine what is the maximum current acceptable, or without burning, without destroying actually the Zener diode. Once you know the IZ, we can determine what is the load current. Now, how we can determine that? You notice that the voltage across RL, that's, the voltage across RL, or the VL, it's equal, or it's the same with the VZ. Means that the VZ divided by RL, it will define, or it will have, the current that flows through the load resistance, which is 100 milliamps. Now, applying one of the two useful equations, you notice that at this node, this junction, I'm having the IP as the IZ plus the IL. means that to find the total current, that's the IT, the IZ minus IL equals 125 for 100 makes 225 milliamps. Okay. Now we determine the IT, we know the Vn and we know the Vz. Again, I'm applying KVL in this inner loop, means that the Vin is the Vr plus the Vz. Now I'm rearranging the equation to determine what is the resistance R. The Vin minus the Vz over the resistance over the current IT. Again, from what is coming this equation, if I'm looking from this one of the two useful equation, we can determine that the VR, or we can rewrite this equation as the Vin as being equally the IT plus multiplied by resistance R plus the Vz. Okay, from this equation, I'm looking to find what is the value of the resistance R, which is the Vin minus the Vz over the current IT. That's why we made this equation to determine the IT or to determine the resistance R if we need in different problems. Means that the Vin minus Vz over the IT gives you a value of the resistance as 22.22 ohms. And I put that in writing from where it's coming. Again, I explain one more time. That's one of the two useful equations in terms of the voltage, the supplied voltage. That's the voltage across a resistance R, and that's the voltage Vz of the Zener diode. Rearranging, and I explained that from what is coming, it's the resistance R as the difference between the input voltage minus the Zener voltage divided by IT. Excuse me. Now, at this point, we covered the first and the second example, and actually, the second type of problems, the useful applications. Useful application that may be used to determine the value of the resistance R, and we determine the maximum and the minimum input voltage for a circuit. The second type of application, or the third type of application is in terms of determining the load resistance. You notice that initial example was a variable input voltage. Now the second example was determining the resistance R, and the last example is to determine what is the minimum and the maximum voltage of the resistance RL. The first two examples again is for a variable input, a resistance R, and now the last example is in terms of a variable resistance. Means that we are looking for look for the RL max, and on the other side is the RL min. Suppose that again. Almost the same information as the previous example. I'm using the 25 volts as the input voltage. Given the VZ as 20 volts, IZK it's 5 milliamps, and we just determined that the IZ max is 250 milliamps. The resistance R is choose as 10 ohms, and the variable load. But again, we have to look for this circuit as that's the circuit, and that's the load. Now the load that is attached, or the load that is connected between the two terminals, has to maintain a constant voltage. Means that the VZ, or the regulator, has to maintain a constant voltage, and in top of that, we know that the current has to be between the two limits. For a full load, again, for the circuit means that I have to determine what is the minimum resistance. In terms of loading a circuit is in terms of the current, means that I'm looking to determine what is the minimum resistance to determine the maximum load for the current. Again, when we are saying, a load for the circuit is in terms of the current, not in terms of resistance. Remember that the load for a circuit is in terms of the current, not in terms of resistance. We know that resistance is inversely proportional with the current. Now we are making the assumption that the circuit is at full load. Now we have to determine what is the minimum resistance that gives the maximum current. Now suppose that we are lowering, we are making the resistance to decrease. The low resistance is decreasing. If the load resistance is decreasing, that's why I'm showing step by step how it will affect the IZ and how it will affect the total current. Means that the IL is increasing. That's the load of the circuit. As the IL is increasing, the IT, again, look for this current, stays constant, means that the IZ is decreasing. Now, if I'm looking back in those conditions, one of the two conditions is to maintain a minimum current flowing through the diode in order to maintain the voltage. Means that going back to this diagram, the graph, means that in order to have the VZ or the Zener voltage, means that I have to maintain, and I mentioned that the current span or the current range between the two limits, the IZK and the IZM. Going back to the equation, now we are at this point, IZ must stay greater than or equal with the IZK. Means that the IZK, it will be the minimum current. Means that the limitations in terms of the IL, we have to determine what is actually the maximum IL current. Now, looking back in the main equation, I said that the KVL, I'm rearranging the same equation in order to find what is the total current, the V in minus VZ over the resistance R, which makes 500 milliamps. That's the total current supplied by the voltage source to the circuit. Now, to determine the maximum current is the IL max. We know the IT, and the minimum current that can flow through the diode in order to maintain the Zener voltage is 5 milliamps. We know that, and it's given. Makes the IL maximum as 495 milliamps. Once the IL max, we can determine what is the minimum resistance value for the load, or the RL min. The VZ, that's the voltage across the RL, divided by the maximum current. You notice that I'm using the maximum current to determine the minimum resistance value, which is 40.4 ohms. Means that I have one of the two values for the load resistance. Okay. Now, when the load is minimum, I'm not saying a short circuit because I cannot short circuit the load. I say that the minimum load for the circuit means that how much I can increase the load resistance, or what is the maximum value for the load resistance. Now, let's see how that goes. The RL is increasing, means that the current IL is decreasing. If the current IL is decreasing, the IZ is increasing. The maximum IZ current is up to the IZ max, means that another limitation in terms of the load resistance is the maximum current. This is the current that the maximum current that can flow through the Zener diode. Now, I have to calculate what is the IL minimum. Again, I'm using the same equation. I'm using the IT minus the IZM. The difference between the two currents is 500 minus 250 makes 250 milliamps. What else we know? If that's the IL minimum, I can determine what is the maximum load resistance. Means that I'm using the minimum load current to determine the maximum load resistance, which is the VZ over the IL minimum, which is the 80 ohms. Means that the resistance RL, or the load that can be attached to the regulator, to the Zener diode, to the circuit, can be anywhere in this range. The minimum resistance is 40.4. That's the RL minimum. The maximum resistance, which is the 80 ohms, and I will define that as the RL max. Now, one more question. You notice that in this example is not given. You may ask, what is the power dissipation or the maximum power dissipation of the diode? Again, to determine the maximum power dissipation, or the PD, I'm using, the maximum current. Always, voltage VZ is the same, is that I can define the PD, or the PD max, as the 5 watts of this diode. Now, going back, to this circuit, and I want to emphasize, that's why I'll try to clean it up a little bit, because there is one more. Okay, I mentioned that, the IT stays constant. That's, the power supply to the circuit. If the IT is constant, I mentioned that if the RL is increasing, means that the IL is decreasing. What is going to happen with the IZ? You notice that the increase in resistance will cause a decrease in the IL. As the IL is decreasing, the IZ is increasing. Means that the IZ, it will change the impedance, which will take, the excess of current that is required if the load resistance is increasing. In the same way, we can look for the RL minimum. If the RL is decreasing, means that the resistance is decreasing, which will cause an increase in the IL current. The IL is increasing. You notice that as the IL is increasing, the total current stays the same, means that the IZ is decreasing. But the limitation, again, is the IZK to maintain a constant voltage across the diode. Now, the question is, if we are exceeding the IZ max, and I'm at this point, suppose that I'm exceeding, the IZ max, what is going to happen with the diode? It will dissipate more power, means that it will overheat, it will burn, or it will destroy actually the Zener diode. That's why the semiconductors are sensitive to temperature. Remember that. As we are passing, a certain degree in the junction, the semiconductor, it will be destroyed. And in this case, we may have a short circuit or an open circuit for a diode. Any questions, comments, concerns? You notice that I will post, the original file that I was working on, and I explain on D2L. That's why I give, some extra explanation during the lecture, but everything is written, everything is on this file. Any questions, please? Next lecture on Friday morning, I will start talking about the special types of diets. It's the thyristor, diac, and triac, and you will see, some advantages of using, these type of diodes. That's, again, specific applications, of the diodes. Any questions, comments, concerns? Just to remind you guys, the Zener diode, thyristor, diac, triac, BJTs and FETs, it's part of the second assignment, second test. Everything up to Zener diode. Zener diode is not included. Aiden, I will mark your assignments and I will try to send it back to you by email because Monday is it's a holiday, it's a Thanksgiving, and I'm not seeing you in lab. That's why I expect an email with a marked assignment from me. I will say Sunday or Monday, the latest time means that you'll have it back before the test. Thank you. Any other questions, please? If you don't have any questions, have a nice day, guys. I will see you on Friday morning. Thank you.